Would you like to lose a little bit of weight without doing any exercise or dieting? Would you like to age just a bit more slowly than your friends? Well, you might be surprised to hear the laws of physics can help.
The key to unlocking these everyday questions is gravity. It sculpts the universe. It warps space and time. It's a fundamental force of nature. But gravity's strange powers, discovered by Albert Einstein, also affect our daily lives in the most unexpected ways. In this film, we'll be using cutting-edge scientific techniques to investigate how gravity changes your weight.
It's gone up.
Your height. I really have shrunk. And even your posture. And with the help of thousands of volunteers, I'll show you how gravity makes us all age at different rates.
Throughout the day, I've just been logging onto the phone, logging onto the app.
As a physicist, gravity is central to my work.
Oh, wow.
And in exploring it, I'll be challenged on how I understand this most mysterious force.
Wow. Okay, I need to go and write this one down.
And I'll have to tackle the very nature of reality itself. Gravity. It binds together all the matter in the universe, and it makes our existence here possible. But in the end, it all boils down to one simple question.
What happens if I drop an object?
Gravity's many mysteries are all contained in this single action: how an object falls. Here's the first puzzle. Why does a hammer fall faster than a feather? You might think it's because the hammer is heavier. But that's not the real reason. The answer is air resistance.
It's not the weight of the objects that matters, it's their shape. And I can demonstrate this very easily with these two umbrellas. They both have exactly the same weight. But if I open one of them, you can be pretty sure it'll drop more slowly than the other one.
In fact, all objects would fall at the same rate if you could only remove the air. The first person to realize this was the 16th century mathematician Galileo Galilei. Famously, it's said he worked it out by dropping objects off the Leaning Tower of Pisa. And he was spectacularly proven right in an experiment carried out on the moon in 1971.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time.
It worked perfectly.
How about that? It proves that Mr. Galileo was correct in his findings.
Now, Galileo was obsessed with a second question too.
When you drop an object, it's actually quite hard to tell if it falls at a constant speed or picks up speed as it drops. Even in slow motion, it's pretty hard to tell.
But Galileo realized this. First, drop an object a very short distance. It lands with very little impact. But of course, drop it from higher up. This time, the ball easily breaks the tile, which means it must have accelerated, gaining in speed and momentum as it dropped. Galileo had identified something fundamental to all falling objects. They accelerate. He realized there might be a way to measure how much falling objects gain in speed. What he devised was the first ever attempt to measure gravity itself.
he built a long wooden ramp, rather like this, that he had sloping at a shallow angle. The idea was to roll balls down the ramp and measure their acceleration. The crucial thing is that the ramp had to be at this shallow angle to reduce the effects of wind resistance. It also meant that the balls would roll down slowly enough to give him time to measure their speed. But the big problem was this: how do you measure time accurately in an age when there were no accurate timepieces, let alone stopwatches? Well, Galileo came up with an ingenious idea involving the flow of water, essentially measuring time from the amount of water collected in a cup. So we're going to try and repeat Galileo's experiment. I say we because I have a couple of willing volunteers, Gavin and Joanna. 3, 2, 1, go.
And stop.
Okay, there's one. Now, if you come down a quarter of the way down the ramp, go.
Stop.
Okay, so now half of the way down, go.
Stop.
Just in time. Okay, and then 3/4 of the way down, go.
And stop.
Right, turn the tap off. Okay, so we have our 4 measurements, and I can see a progression from fuller to emptier. But what we need to do now is find the mathematical pattern by weighing carefully the water in each glass.
Weighing the water should give us an idea of how long each roll took. And in our experiment, these were the results. Now, there's one immediate thing you can tell. The ball really sped up the longer it rolled. In fact, our results seem to show that the time it took to cover the first quarter of the ramp was about the same time it took to cover the next 3 quarters.
Right.
So we have a strong hint of a mathematical pattern. Now we'll see if we're right by placing bells along the ramp at intervals which are based on the results.
Okay. This arrangement looks a bit strange because the gap between the first 2 bells is much shorter than the gap between the 3rd and 4th bells. But that's okay, because if we've got our calculations right, the ball starts off slowly, so it covers a shorter distance, and as it picks up pace, it'll cover longer and longer distances. So we should hear the bells ringing at equal intervals in time. Go. Beautiful. So, what does this all mean? What's the mathematical formula? Well, this is something that Galileo worked out. Let's say, from the start, the ball covers a distance of 1 meter in the first second. After 2 seconds, it'll have covered 4 meters. After 3 seconds, 9 meters. After 4 seconds, 16 meters, and so on. If you recognize this progression, you'll see that distance goes like the square of time.
Galileo had found the rate at which gravity speeds up objects. And he'd found another fundamental principle. You can measure the strength of gravity by how much it causes falling objects to accelerate. Detecting gravity has become exceptionally sophisticated these days, but still uses exactly the same principle. This is Hurstmonceau Castle in Sussex, and in its grounds lies the Space Geodesy facility. Here, Vicky uses an astonishingly sensitive instrument to detect the exact strength of gravity on this one spot.
Okay, so Vicky, tell me about this incredible gravitymeter that you work with.
Okay, so this is the dropping chamber in a stripped-down version. So essentially what happens is you've got a cart that gets raised to the top, and then the cart accelerates away from a mass in the middle. And so this section here lifts off, and as it drops under free fall.
So this component in the middle, as it drops, is basically just Newton's apple falling to the ground.
Yes.
So this is a stripped-down version, but that's the real thing.
This is the real thing.
How does it actually work?
In here it's a vacuum.
So there's no wind resistance
So
as
there's
it
no
falls,
wind resistance.
right?
Inside, a laser is used to measure exactly how fast the mass is accelerating.
This is the 21st century version of Galileo's ramp and the balls rolling down. So can we get it going?
Of course, if you'd just like to press the button on the laptop.
This one?
Yep.
Okay.
So it's now communicating with it.
Oh, here we go.
There we go. So it waits 5 seconds, then takes a measurement of gravity.
And
repeats.
again. Oh, and you can see all the results appearing now.
Yep. Each of those green dots is a measurement of gravity with the actual number that it's getting for each one.
The unit Vicky uses has a familiar ring.
I see that the number up at the top here. So you've got this unit, microgal.
Yes, gal is essentially 1 centimetre per second squared. The gal was named after Galileo.
So we've just taken the measurement of gravity here today, and it's this highly accurate number, 981124007 microgals.
The reading means that the Earth's gravity speeds up a falling object by around 9.81 meters per second for every second it drops. Vicky tells me something intriguing. She takes a reading here every week, and she's found that the strength of gravity changes by tiny amounts over time. Heavy rainfall, for example, can cause gravity to increase slightly.
Presumably, if gravity is changing here in one spot, it'll have different values all around the world. And so you can have a gravity map of the entire planet.
That's right, yeah.
So what's the reason for these strange fluctuations? That's what I want to investigate next.
So, gravity changes as we move across the surface of the Earth. Well, this lies at the heart of a challenge that I've set 2 young volunteers. I've given them a task to try and find the place in Britain where gravity is at its weakest, so where objects would weigh the least. And I've given them just 3 days to try and find it.
The volunteers are Estrella Sendra, a PhD student.
I've been living in London for 5-6 years, and I'm originally from Seville in Spain. I'm very interested in taking part in this project because I would really like to know more about how this world works.
And Poppy Begum, a journalist who lives in London.
I did my degree in biomedical science, and I did biology and chemistry for my A-levels, but I haven't done any physics since I left school. I'm fascinated to find out more about gravity, and I actually enjoy a puzzle. I like a challenge.
Now, the team can't just weigh themselves to see changes in gravity. Body weight fluctuates naturally by a couple of kilos over the course of a day, whereas changes due to gravity as they travel around the country are going to be tiny in comparison, a matter of a few grams. So they're going to have to use sophisticated scientific methods if they want to measure gravity accurately.
And that's why the volunteers will be joined by 3 specialists in gravity science. PhD student Sonak Bose. He'll be in charge of some very sensitive measuring apparatus from the National Physical Laboratory. Sean Hughes, a geologist, who'll be using a portable gravity meter. And Andrew Ponson, a cosmologist at University College London, who'll help interpret the results. We've taken a collective weight for the team before they set off. It's 380 kilograms. So can they find the place in Britain where that'll decrease? They're setting out in Snowdonia National Park in North Wales. The railway climbs from here to the 1,000-metre summit of Snowdon. Sean takes his first gravity reading.
The inside is a mass on a beam, and you turn this counter, this dial, until you get the beam central.
By counting the number of turns of the dial, Sean can calculate the downward pull of gravity acting on the mass inside the machine. Sonak has a simpler method.
So inside the box is a 2-kilogram mass, and it's supposed to be sort of as perfectly 2 kilograms as it's possible to get. All right, and place it here.
Oh, It's just coming under, isn't it?
1998.2 grams.
So it was 2 kilos in the laboratory, but now here it's a bit less.
It's the first puzzle. Why does a 2-kilo mass tip the scales at just under 2 kilos? And it's one which gets straight to the heart of what the challenge is really about.
Mass is often confused with a related quantity, weight. The mass of these dumbbells is fixed, it doesn't change. It's a measure of how much stuff they contain. Weight is different. It's a measure of the effect of gravity on these dumbbells, the downward force pulling them to the ground in the same way that it's keeping my feet firmly stuck to the ground. The crucial difference is this: if I was holding these dumbbells on the moon, they'd still have exactly the same mass, but they would weigh 6 times less because the moon's gravity is so much weaker than the Earth's.
So that's why Sonak's bringing along the 2-kilo mass. If it changes weight, then this should mean that gravity itself has changed. Ahead of them is the summit of the highest mountain in England and Wales, famed for its stunning scenery. Or it would be stunning if you could see it.
And this is what we came all the way up here for, this amazing view at the top of Snowdon. You wouldn't know it, but honestly, we are here.
So we're now near the summit of Snowdon, and I've set up the gravimeter again, and we're going to see what the difference in the reading is.
He has to turn the dial again and again to try and get a reading. It's clear gravity has changed, but which way? Has it got stronger or weaker? The team leaves Sean to work out his results and tries to position the scales as close as possible to the summit. But the reading is all over the place.
Oh,
It's gone up.
So it's fluctuating quite a lot due to the wind.
I have to say, this is what science is always like, isn't it? It's never quite what you want it to be.
So they head inside to the cafe next to the summit.
The wind was being a bit naughty, but hopefully,
I mean, now it's in
it's gonna work
0,
fine.
so it should be all right.
1998.2 down there, 1997.8.
There you go.
We've got it.
That's 0.4 of a gram off.
The mass weighs a tiny bit less. It's lost about 1/5000th of its weight. And Sean's found that gravity itself has reduced.
At the top of the mountain, we took the measurement, and we discovered that the pull of gravity had gone down. It had gone down an equivalent of 206 turns of the dial, and we worked out that that's equivalent to 219 milligauss.
So it's clear from the team's measurements, gravity weakens as you go higher, and you get a bit lighter.
It's just an excuse to say, where are we, like the lightest? Who cares? But in the sense that
Who does care?
it's actually really interesting. It's like an illustrative example of seeing how this is actually fluctuating depending on different factors.
Yeah,
And
absolutely. And that we could measure it and we could see it with our own eyes. It actually makes you think about gravity in a very active way. It's such a fundamental force phenomenon in nature, but we don't know much about it.
But why does gravity change with altitude? To understand that question, you have to get to grips with the extraordinary discoveries of the next scientific giant in our story, Isaac Newton. Born in England in the middle of the 17th century, he spent his life wrestling with so many apparently separate questions, from why things fall to the ground to why planets orbit the sun.
It took the genius of Newton to realize that there was one single equation that could answer all these questions. And here it is, his famous law of gravity. It might look complicated, but this is one of the most important equations in the whole of science. F here is the force. Now, Newton said there's an attractive force between any two objects in the universe. On this side of the equation, G we call the gravitational constant. Now, Newton knew it had to be there, but he didn't know what its value was. M1 and M2 represent the two objects, and r is the distance between them. Now, the equation tells us that the more massive the objects are, the bigger m1 and m2, the greater the attractive force. But the further apart they are, the bigger the value of r here, the weaker the gravitational force.
With Newton, what was once mysterious now became clear.
Newton's equation describes why an object falls to the ground, including his famous apple. But its true genius is that it applies to any object, anywhere in the universe. So it's a very simple and elegant way of describing some of the seemingly most complicated phenomena in the cosmos.
His law of gravitation can still be used today to explain how orbits work, to predict when a comet will return, to describe why galaxies spin, or to slingshot spacecraft around planets. Newton tells us to look for the underlying simplicity in natural phenomena. For instance, how the moon orbits the Earth.
If I let go of this apple, it'll fall straight down because of the pull of Earth's gravity. But if I throw it, to begin with, it travels in a horizontal direction, that's the direction of travel, but Earth's gravity is still pulling it downwards, so it ends up following a curved path. Now, if I throw it harder, it'll travel further before it hits the ground. And in principle, if I could throw it hard enough, I could put it into orbit. And that's exactly what's happening with the moon in orbit around the Earth. It's a combination of wanting to travel in a straight line, but also being pulled down by the Earth's gravity. So it ends up constantly falling around the Earth and constantly missing.
Newton's famous equation also explains the strange effect which the road trip team has discovered, that objects get lighter as you gain in altitude.
When I weigh myself, I'm represented by the first mass, m1. The second mass, m2, is the Earth itself. And the force pulling me down, my weight, depends on the distance between me and the center of the Earth. And that's the secret of the road trip. If you want to find a place where you weigh the least, then you have to get as far away as you can from the Earth's core.
So it's the afternoon of day one, and the road trip team have to work out where to go next. Poppy and Estrella have a good idea. Find somewhere higher than Mount Snowdon.
From the measurements that you guys did at Mount Snowdon, altitude clearly plays an important part in gravity. So with that in mind, we've got to go to the highest point in the UK, which is Ben Nevis.
OK, but there's just one thing that we haven't shown you so far. We actually brought along an extra experiment. So can we please show you this first before you make the final decision?
Yes.
Sonak actually has the other part of this experiment. We always carry around
some power tools, as physicists always do. So let's start off nice and gentle. OK, and then try and pick up some pace.
Pizza.
And
you got some pizza there.
Point proven.
The point is that when something is spinning, it kind of gets flung outwards.
Yeah.
And you can actually use that to make a nice flat piece of pizza. But this also applies to the Earth.
The Earth isn't perfectly round. It's what's known as an oblate spheroid. It bulges at the equator where the spin is greatest.
We've kind of got two competing effects now. We're trying to get away from the centre, the actual core of the Earth, the point at the very centre of this ball. But now we can do it in two ways. We can either kind of go up something tall, or we can just go down towards the equator.
This is what we find when we're doing gravity surveys, is that as you move south, there tends to be an effect from latitude, which is often usually larger than the effect from altitude.
So the closer to the equator you go, the further you get from the Earth's core, and the lighter you get.
So, guys, the sun's setting just behind me here. This is north. From the conversations we've just had, it sounds like we've got to go that way down south. Is that right?
Yep. Yep. Okay. Let's go.
Let's go.
The team is starting to uncover the reasons why gravity changes as you cross the surface of the Earth. Our planet is defined and shaped by the complicated forces which act upon it. And detecting tiny fluctuations in its gravity field can give us important clues. It can help us understand how our world is changing. The Space Geodesy Facility at Hurst-Monceau is one small part in an enormous global network, which uses satellites to detect the tiniest of changes in the Earth's gravity field.
Tell me what exactly your job is here.
What we're doing with this telescope is measuring very accurately the distances of satellites from here. So we're using very short laser pulses, which we direct towards the satellite. On the satellite, there are reflecting cubes, which return some of that light to us. And we measure how long it takes the light to go to the satellite and back.
And how far away is the satellite
typically? The one we're tracking now is one of the Galileo satellite, which is about 20,000 kilometers.
20,000 kilometers
Yes.
away?
Yes.
Okay, so we've got it aimed at the Galileo satellite, and you're going to turn the laser on now?
Yes.
Oh, wow. And that laser beam that's being fired up towards the satellite, the time it'll take to get there and come back again, it's a fraction of a second, isn't it?
It is. It's about 150 thousandths of a second, 150 milliseconds. And we're sending about 1,000 of those per second.
This strange-looking object is based on satellite readings. It's a highly exaggerated representation of how Earth's gravity field varies over time. Fluctuations like these can give us important insights into climate change. Ice caps melting, sea levels rising, changes in groundwater. All of these have an effect on the local strength of gravity.
So something as important as climate change, in order to understand it and do something about it, we need to know the distribution of the gravitational field of the Earth very accurately.
Absolutely, yes, and it's a global measure that we need.
For the road trippers, it's the start of day 2. And they're heading for the south coast. They're stopping off in Herefordshire. It's a good location, as it's the same altitude as the base of Snowdon, but they've moved about 80 miles further south. So if they find gravity changes here, it must be due to latitude.
It's not a huge difference, but it's noticeable. Our counter reading at the bottom of the mountain was 4,840.
Yeah.
Our counter reading here is 4,717.
All right, so we do get to see a difference.
So we're actually at the same altitude as the base of Mount Snowdon, but because we've travelled further down south overnight, gravity's less here.
Yeah.
They push on. And by sunset, they reach Sidmouth on the south coast. Sean takes the second gravity reading of the day. And Poppy improvises a map. Well, sort of a map.
Can we write not to scale at the top there? So I drew this map. Scotland's a bit squashed. Wales is quite high up, and Cornwall is there, but you get the idea. So, Sean, we've been travelling with you. You've done quite a few gravity meter readings. Can you plot them on this not to scale badly drawn map, please?
Sure. So if you remember, we started off in Mount Snowdon, about here, and that was the 0 measurement for our survey. And then we've come all the way down here to the south coast. The difference from the base of Snowdon is minus 212 milligals.
Wow.
So the difference between measuring gravity at the base of the mountain and the top of the mountain is about the same as here at this latitude and down here at this latitude.
They're quite clearly at sea level, yet gravity here is roughly the same as it is at the top of Snowdon. But where next?
We are here if we want to find out where we are the lightest, why don't we travel all the way to the most southerly point in the UK, which is here?
But altitude can also help us. So why not find a place in the country that is both low in latitude, but also is high in altitude in terms of height above sea level? Because that will get us somewhere that is really far away from the core of the Earth, whilst staying within the country.
So, the answer to the puzzle lies in a combination of two factors. How much further south should they go, and how much higher? At the end of day 2, Sean's results show that the team weighs about 80 grams lighter in total than back at the base of Snowdon. The way that weight changes is just one example of Newton's famous equation in action. But Newton had left his masterpiece incomplete. He didn't know the value of G, the gravitational constant, which sets the size of the force. To harness the full power of the equation, you need to know G. And the vital clue came with an incredible experiment conducted in London at the end of the 18th century. It was an attempt to work out the mass of the Earth itself. And it was carried out by an eccentric, extravagantly rich aristocrat, Henry Cavendish.
Cavendish was a chronically shy, deeply solitary man living in total isolation in his house in Clapham. The story goes that one day he accidentally bumped into a female servant on his staircase. He was so traumatized by this event that he had a new staircase built just for him, so this horrible incident could never happen again.
Cavendish had inherited vast fortunes and was able to dedicate his life to devising pioneering experiments, including one particularly extraordinary piece of equipment.
He set up something a bit like this. It's called a torsion balance. It involves 4 lead spheres, 2 large heavy ones which are held fixed in place, and suspended by a very thin wire is a wooden rod, 6 feet long, with 2 smaller balls on either end. Now, the crux of the experiment is the relationship between the large ball and the small ball. Now, of course, there's a gravitational pull downwards on both of the balls due to the Earth's gravity. But Newton also tells us that there should be a very weak gravitational pull between the balls. And this is effectively what Cavendish was trying to measure. Any slight movement of the small ball towards the large one should cause a twist in the torsion wire. And that's what Cavendish was trying to detect. Of course, this is all much easier said than done. The experiment was incredibly sensitive. The tiniest of vibrations, the slightest breeze, changes in temperature could all influence the measurements. So Cavendish had to isolate the apparatus inside a box and the box within a shed. He even realized that his mere presence next to the apparatus could influence things, so he had to remove himself outside the shed. What he then did was sit outside the shed and through a small hole in the shed wall, look through a telescope to detect the tiniest of twists in the wire. It was an incredibly difficult process, but after many months, he finally felt confident enough that he had a reliable result.
Cavendish found that the small balls did move. A tiny 4 millimeters. He calculated his results by comparing the density of the balls with the density of water.
In the end, the result of Cavendish's experiment and subsequent calculations was that the density of the Earth was about 5.5 times that of water. Or, put another way, the mass of the Earth was 5.9 trillion kilograms. What's most remarkable is that Cavendish got this number right to within an accuracy of 1%.
With Cavendish's astonishing result, scientists were able to work out G. Then the equation could be used to determine the mass of any celestial body in orbit around another. So astronomers were able to calculate the mass of the Sun, and the planets, and the Moon, and eventually even distant galaxies. And of course, back on Earth, we never escape gravity. Over the course of the day, it actually squeezes your spine, an effect you can see for yourself if you use a measuring rod.
Okay, so it's 7:30 in the morning. I've just got up and I'm going to see how tall I am before gravity drags me down. That's 178 centimeters, or just over 5'10".
Over the course of the day, gravity compresses the fluids in your spine.
Right, it is just past 11 p.m. I've been standing up for most of the day, so let's see if gravity has had an effect on my height. That is 176 centimeters, so I really have shrunk by just over half an inch over the course of today.
In the longer term, gravity can affect your posture permanently. But there are exercises you can do to counteract this effect.
Part of my research has been looking at the effects of gravity on the human body. So people might not be aware, or they might not always think about the effect of gravity on our physical state, on our health, and particularly on our posture. However, because it's such a constant force, gravity has a massive impact over the course of our lifetime.
As you get older, you can develop a stoop, which is damaging to your mobility.
Gokul here has actually got very good posture, but I'd like you to just show not so good posture. So when poor posture is really rounded shoulders and then loss of the curve in the back as well. Can I just ask you to raise up your arms when you're in that posture? So, no, and then just come back down, shoulders back into them, and then raise your arms. You can see the effect of posture on function.
Ironically, the exercises which many gym goers do actually make your posture worse. That's if you only exercise the frontal muscles, like the chest and abdominals. So it's recommended you exercise the back muscles just as much, to straighten you out and counteract the effects of gravity. Meanwhile, it's the end of day 2 for the road trip, and they've reached Sidmouth on the south coast, looking for the place in Britain where they'll weigh the least. They've worked out the answer lies in a combination of 2 factors: the right mix of going south and being higher up. And for the final leg of the journey, I'm going to meet up with them. I asked them to drive a short distance west to one of the most remote areas in mainland Britain, Dartmoor National Park. It's only 40 miles from the southernmost tip of Britain.
Hello! Hi, Andrew! Nice to see you!
And it's very high, very hilly territory.
Jim, the team got to the south coast yesterday, where we defined gravity at its weakest. But we haven't quite figured out whether it's altitude or latitude. Do we go further south, or do we go higher up?
You're right to ask, do we go as far south as possible or as high as possible? That's why I've brought you here to Dartmoor, and we've charted the most important points on this map here.
All right.
Let's have a look. So we are here, 2 bridges.
Yeah.
These 4 dots represent these hills up there behind us, which are at about 500 meters above sea level. So that's what we want to check out.
These hills are close to the south coast, and they're also the highest in the whole of the south of England. So logic suggests there must be the right combination of latitude and altitude.
Well, there's another reason why this makes perfect sense, one which we haven't looked at yet, and that is the effect of the underlying rocks on gravity. And I've got a map here that shows...
You're going to trump my map with yours, aren't you?
Here we are, down here. Now, these blue areas are the lowest areas according to the density of the rocks underneath.
The rocks around here are made of granite, which will make gravity weaker still.
So that's helping as well as the altitude and the fact that we're further south.
Yep, it's also playing a part.
Well, we have a plausible theory, but now we need to test it. If I'm right, then at the top, our gravity reading should be by far the lowest reading of the trip. Of course, there's another effect of gravity to deal with now. It's knackering when you head uphill.
Okay, so I think this is pretty much the start of the hills we've located on the map. So let's see if this is the lightest place. Sean, if you want to get the gravity meter out, and we'll take another reading here.
Yep.
Okay.
Sean sets up his equipment one more time.
What's the news?
Well, at the bottom of Mount Snowdon was our zero for this test. We found we lost a certain amount by going up to the top of Mount Snowdon. We found we lost a certain amount coming south to the south coast. Not only have we beaten that, we've smashed it.
Brilliant.
We were minus 219 milligals lower at the top of Mount Snowdon. Here on Dartmoor, we're minus 347 milligals lower.
Wow. Brilliant. So it is a combination of three things. We're far south, so that's the latitude. We're at altitude, we're quite high up, and we're surrounded by all this granite rock, which is low density anyway. I hope you all think it was worth the climb up here anyway.
Yeah, absolutely.
There you go. Boom. Science.
Now, we already know that the altitude of these hills takes us much further from the Earth's core than anywhere else further south in Britain. So gravity must be weakest here. There's extra evidence too. The British Geological Survey has compiled tens of thousands of gravity readings made in the UK, and the lowest readings ever recorded were all taken around here, on the high hills of Dartmoor. What do we do to celebrate? We weigh ourselves, of course.
The FX weight that much.
It's all them Nutella pancakes for breakfast.
I need to lose weight. I can tell you that you should weigh something like 20 grams less than you did at the base of Mount Snowdon. Guys, I'm guessing something like 25 to 30 grams less. So if you want to weigh as little as possible, this is the place in Britain to come. But in any case, it's such a tiny amount that it's going to be wiped out entirely by whatever it was you had for breakfast this morning.
In episode 2, I'll investigate how Albert Einstein's theory of gravity completely changed our understanding of space and time. I'll travel to Louisiana in the USA to listen to the sound of black holes colliding.
Biggest source of energy in the universe, one of the biggest events you'd ever measure, and we just barely saw it.
And with the help of thousands of volunteers and a smartphone app, I'll explore how the science of gravity can help you age slower.
Would you like to lose a little bit of weight without doing any exercise or dieting? Would you like to age just a bit more slowly than your friends? Well, you might be surprised to hear the laws of physics can help.
The key to unlocking these everyday questions is gravity. It sculpts the universe. It warps space and time. It's a fundamental force of nature. But gravity's strange powers, discovered by Albert Einstein, also affect our daily lives in the most unexpected ways. In the previous episode, we used cutting-edge technology to investigate how gravity changes your weight.
It's gone up.
Your height.
I really have shrunk.
And even your posture. In this show, with the help of thousands of volunteers, I'll show you how gravity makes us all age at different rates.
Throughout the day, I've just been logging onto the phone, logging onto the app.
As a physicist, gravity is central to my work.
Oh, wow.
And in exploring it, I'll be challenged on how I understand this most mysterious force.
Wow. Okay, I need to go and write this one down.
And I'll have to tackle the very nature of reality itself. Gravity. What goes up must come down. All of our lives, we abide by its rules. It dominates our every action. But there's one select group of humans who know what it's like to live free of gravity.
2, 1, 0. Liftoff.
Everybody's used to gravity. We're used to the oppression of it. Gravity is the ultimate oppressor. It grinds us under its heel 24/7 with no release until you're in space. And then suddenly you're free from gravity. You're weightless in orbit.
Canadian astronaut Chris Hadfield spent 5 months on board the International Space Station.
You can pull your knees up to your chest and just tumble. Or if you take a wet cloth and you get it dripping wet, and everybody on Earth knows what'll happen when you wring it out. All the water will fall inevitably. If you do that in weightlessness, the water stays there, and it actually, because of the surface tension, starts crawling up your arms. It's a little bit mesmerizing and hypnotic to be in weightlessness. If you're weightless, you don't need a bed. You don't need a mattress. You don't need a pillow. Your body is floating completely suspended like magic. Movement becomes effortless. You can push off with one finger and fly and tumble. You don't need to hold yourself where you are with muscle. You can just, with a delicate fingertip pressure, you can stay where you are.
Okay, separation confirmed. Timer is on.
Backing away at a rate of just a little over 1/10 of a meter per second.
Re-entering gravity is a punishing experience.
To come back to Earth is violent. It can be 5 times the force of gravity or 8 times the force of gravity, crushing you down into the floor of the ship for quite a long time. Then, of course, you hit the ground and tumble and roll to a stop, and now you're the victim of your past. You're the victim of your decision-making, lying there, trying to shake your head and get used to being in gravity again. I remarked at the time that I had forgotten that my lips have weight and my tongue has weight. You don't think about it. But if you try and talk articulately standing on your head, you'll notice that you have to sort of control your lips and your tongue a little differently just because gravity's pushing them the other way. And it's the same sort of thing, raising your arm, holding your head up, turning your head when everything wants to tumble, just keeping your balance, all of those things. It's a little bit like relearning to walk again, like an infant.
Gravity shapes our bodies and molds our planet. Nothing happens on Earth without its power and influence. Sir Isaac Newton explained so many of its effects using one simple equation. And in the centuries that followed, his laws of physics led to breakthrough after breakthrough, spurring on the Industrial Revolution. But in the first decade of the 20th century, the next genius in our story challenged the very foundations of our understanding of gravity. A young German scientist called Albert Einstein was churning something over in his mind. he thought that something in Newton's laws didn't quite add up.
Imagine I'm the sun, and this tennis ball is the Earth in orbit around me. Newton's laws can describe very precisely the path the Earth takes around the sun in terms of the mutual gravitational attraction between the two bodies. But what Newton can't explain is what connects them. In reality, of course, there is no invisible string between the Earth and the sun holding the two together. There's just empty space, a complete void. And yet, according to Newton, the Earth and sun pull on each other instantaneously across a vast distance. How can gravity act in this way when there's nothing to connect it or transmit it?
After years puzzling over this, Einstein had a blinding flash of inspiration. Just like Galileo and his ramp, or Newton with his apple, Einstein's breakthrough came because he was thinking about one simple action. What happens when something falls? To explain, I'm visiting this 400-foot-high tower in Northampton, built to safety test lifts.
One day in 1907, Einstein had what he called the happiest thought of his life. What if I was standing in a stationary lift, completely isolated from the outside world, not feeling anything apart from the pull of gravity on my feet? What if then the lift cable breaks and I start falling? What are the forces that I will feel as I'm plummeting to the ground? Well, I'm not going to try that. Fortunately, there's another way to test this without me having to plunge down a lift shaft. Sorry to disappoint you. This little device here that I've strapped to this plastic toy is an industrial accelerometer, so it measures acceleration. Now, I've got it connected to my laptop, and it's showing a measurement of 1g. Now, that's the downward acceleration due to the pull of Earth's gravity. So basically, it works just like a gravity meter. But what happens if I were to drop it? Presumably, it'll carry on measuring 1g because it's falling in Earth's gravity. Okay, well, let's try that and see. So you can see here along this line at the bottom, that's when I was holding it still, and it's measuring an acceleration of 1g. These oscillations here is when I stood up and there's a bit of disturbance, but this spike along here is the moment I released it. And this short duration along here is the time it was falling. And you see, while it was falling, it was registering an acceleration of 0. Now, if you think about it, this is really odd. The accelerometer is accelerating downwards, it's plummeting in the full grip of Earth's gravity, and yet it's measuring no acceleration at all. It's as though gravity has completely disappeared.
Einstein's insight was that when something falls, it no longer feels the pull of gravity. In fact, falling is like floating in empty space. This is the essence of Einstein's happy thought, and what we now call his principle of equivalence. Einstein's point is that when the man in the lift falls, he doesn't just feel weightless, he is weightless.
Einstein said the man feels no force pulling on him because there is no force pulling on him. Gravity doesn't act on him, it acts on the space and time around him, what we now call the geometry of space-time.
This was a radical redefinition. Einstein says forget the idea of gravity as a force acting mysteriously between two objects. Now we have to think of it as the shape of space-time changing.
You see, Newton saw space and time as independent, fixed, and immutable. That three-dimensional space is the stage in which things happen. But time is separate. It ticks by at the same rate everywhere in the universe. According to Newton, an object would travel through space in a straight line unless acted upon by a force like gravity that will cause it to deviate from that path. But Einstein said that space and time aren't fixed and immutable. They're interconnected, meshed together in what is known as space-time. And he said that space-time can be warped, that matter curves space and time around it.
So after Einstein, we no longer see gravity as an invisible string pulling objects together. Instead, a body like the Earth warps the structure of space and time around it. And an object in orbit follows a path which is as straight as possible through that space-time. It's a fundamental part of Einstein's vision of reality. Space and time can't be disentangled. You can't talk about space separately from time. So matter warps time as well as space. It's known as gravitational time dilation, and it's possibly the strangest of all of Einstein's discoveries.
I've got two identical clocks here. Now, because the clock lower down is closer to the center of the Earth, it feels ever so slightly a stronger gravitational pull than the clock higher up. Einstein's theory says that the lower clock will tick by at a slightly slower rate than the higher clock. Basically, gravity slows time down.
It's an extraordinary conception of reality that Einstein describes. Space is being curved and time is being distorted. So why can't we perceive this in our everyday lives? Einstein had a rather nice way of explaining it.
Most of us have had the experience as children of trying to work out what our parents do for a living. Well, imagine your father is Albert Einstein. When he was about 12 years old, young Edward Einstein asked his father why he was so famous, what he'd discovered. Well, this put Einstein Sr. on the spot, but he came up with a beautifully simple analogy.
Einstein told his son, when a blind beetle crawls over the surface of a curved branch, it doesn't notice that the track it has covered is curved. I was lucky enough to notice what the beetle didn't notice.
This is what Einstein meant. The beetle is free to move in any direction on the branch. It can move forwards, backwards, left and right, but it has no concept of a direction up off the branch. It's as though, for the beetle, the universe is missing the third dimension. The beetle may think it's moving in a straight line along the branch, but we can see that the surface it's walking on is itself curving and twisted.
Einstein's point was that what we see as the twists and curves of the branch feel to the beetle like forces, pushing and pulling it.
Okay, so consider this rather strange example. Imagine we have two beetles perched on this pumpkin, and for whatever reason, they want to walk up towards the top. Now, if they start at the equator, pointing due north, as they walk, they will begin by moving parallel to each other. That means their paths should never meet. But as they get closer to the top, their paths get closer together. Now, if they're clever beetles, they might try and figure out what's going on, and they could imagine that there's some mysterious force that's pulling them closer together. But for us, from our perspective, we can see there is no such force. All they're doing is following straight paths
over a curved surface. Just as the beetles have no sense that the surface of the branch is curved, we completely fail to perceive the bizarre ways that gravity shapes the reality we live in. Einstein's problem was proving that he was right. After years more thought, he realized that there was a way. By looking far out into the solar system. Incredibly, here in the grounds of Hurstmonceau Castle is housed one of the original telescopes that were used to prove Einstein was correct.
In 1915, when Einstein developed his general theory of relativity, it was just that. It was a theory. It had no proof. In fact, many people found it completely outlandish. But then just 4 years later, in 1919, this telescope, and allow me to geek out a bit here, and I'll give it its correct name. This is the 13-inch astrographic refractor. This telescope proved that Einstein was in fact right, that gravity does curve space itself.
Since then, observation after observation have confirmed that matter curves space and slows down time. So the simple question of why things fall the way they do has led us deeper and deeper into the very nature of space and time itself. Gravitational science shows us how galaxies, stars, and planets form. By measuring gravity, we've discovered the existence of dark matter, that 80% of the mass of our universe is invisible, and we don't know what it's made of. And we've detected exotic objects with extreme gravity, like neutron stars, which have more mass than our sun, yet are only 20 kilometers across. But it's another mysterious aspect of Einstein's universe that I want to explore in my next gravity project. Here at the University of Surrey, some colleagues and I have been working on it for months.
What we're doing is devising a nationwide citizen science project. We're developing a smartphone app that uses the GPS contained on your phone to explore one of the strangest properties of gravity, how it affects the rate at which we age.
I formulated the equations myself, and a small team of computer scientists and software developers is using them to devise the app. Einstein discovered that as gravity changes, so does the rate that time ticks. This means the strength of gravity you feel affects how quickly or slowly you age. The aim of my app is to demonstrate this effect. It works by using a phone's GPS data to estimate your local gravity. And it also calculates the average speed at which you move, because this too affects the rate at which you age. It then uses the equations I've written, which are based on Einstein's theory of relativity, to calculate overall how fast or slowly you're aging. Once the app is ready, I tweet about it. Thousands of people download it, and we start to gather results from across the country. Some people send me videos giving me their results. How fast they're aging compared with how time ticks out in space in zero gravity.
Over the past day, I have aged less by about 172 microseconds.
I have aged less by 10.02 milliseconds.
So since downloading the app, I have aged less by 1.14 milliseconds.
Since opening Time Warp, I have aged less by 2.6 milliseconds.
Our aim is to use their results to build up a map of how time flows because of gravity. My smartphone project provides just one insight into the space and time which Einstein's theories describe. Gravity and its strange ways have given us astonishing insights into the dark secrets of our universe. Perhaps the weirdest objects in the universe are black holes, collapsed stars whose gravity is so strong that not even light can escape their grip. Now, for the first time ever, their effects have been felt on Earth, and they've been detected through the medium of gravity itself. It's a story that has revolutionized the study of modern cosmology.
1.3 billion years ago, in a galaxy far, far away, two black holes swirled around each other, drew closer and closer together until they finally collided with incredible violence. In that final fraction of a second, at the precise moment that they merged, a disturbance was created that sent ripples out through the universe.
Gravitational waves are a key prediction of Einstein's theory. Matter doesn't just curve space-time, it can cause waves, ripples which expand outwards, exactly like a stone dropped in water. This particular wave was unimaginably large. The energy released was greater than all the light being given out by all the stars in the universe.
The wave rippled through space at the speed of light. In 1.3 billion years, it covered a distance of over 10 billion trillion kilometers.
Until, on the morning of the 14th of September, 2015, it arrived here. The streets and cafes of New Orleans, in fact, everything in America and on Earth, expanded and contracted very, very slightly as the wave passed through. No one noticed, as by the time it arrived here, the distortion was phenomenally tiny. Except that one science laboratory did notice. And I'm going to see it. 1,000 scientists across the world are collaborating on it. It's the culmination of over 50 years of effort and is one of the most sophisticated experiments ever devised by humanity. So I'm pretty excited to see it.
It's a rather unusual setting. Here I am in the middle of rural Louisiana, about an hour's drive outside New Orleans. I don't expect to find such a multi-million-dollar cutting-edge research facility as this. And yet, this is the place where recently one of the most important scientific discoveries in human history was made. This is LIGO.
The Laser Interferometer Gravitational Wave Observatory is an enormous construction shaped like an L, with a sophisticated laser system bouncing up and down the two arms.
So we're standing on top of one of LIGO's two arms. This is the first LIGO arm. And in that tube, there's a laser beam that we bounce back and forth between a mirror in the end station and a mirror in this building. And the other bit goes that way, 4 kilometers, perpendicular to the arm we first saw.
This is the L shape.
It's a big L on the ground. So the light bounces back and forth in that arm and bounces back and forth in this arm. And what we actually measure with LIGO is the length of this arm as measured by the light between the two mirrors, and the length of that arm as measured by the light between two mirrors. And then the laser interferometry measures the difference between those two arm lengths.
So as the gravitational wave passed through, the lasers picked it up. They detected that LIGO's two arms changed in length to a very, very tiny degree.
The signal that we saw was just a few thousandth of the size of the atomic nucleus. It's the biggest the signal ever got.
So far, far smaller than the size of a single atom.
Oh, much, much smaller, yeah, that would.
And you need something this huge to pick that up.
That's right. And so this is one of the most biggest source of energy in the universe, one of the biggest events you'd ever measure, and we just barely saw it.
The LIGO scientists turned the gravitational waves into sound waves. So what you're about to hear is, in a very real sense, the sound of two black holes colliding.
It was the first observation of any kind of pairs of stellar mass black holes. Stellar mass means, you know, several or a bunch of suns in weight. And so we learned that they exist. We learned that there are enough of them that occasionally they run into each other and coalesce. And we also learned by comparing the waveform we observed with general relativity calculations that general relativity is, as far as we know, dead on right.
The long concrete bunker to my left houses the beamline, one of the LIGO's laser arms. The detail and the effort that's gone into isolating the beam from the outside environment reminds me very much of Cavendish's famous experiment. He too had to worry about isolating his experiment from external disturbances. Only, of course, LIGO takes things to a far, far greater degree.
Inside the arm is one of the largest and purest vacuums in the world. Atmospheric pressure in there has been reduced to 1/1,000,000th of the pressure outside. The mirrors inside are so reflective that they only absorb 1 in 3 million photons. And at the end of my little trip lies a British success story.
Well, I made it all the way to the end of one of the LIGO arms. To be honest, it took me a bit longer than I thought, especially in that thing. But housed inside this building is one of the reflecting mirrors that bounces the laser beam all the way back down the 4-kilometer arm to the main control center. And the technology that went into developing these mirrors is quite remarkable. It was developed in the UK at the University of Glasgow.
This is what the mirror looks like. Its surface is extraordinarily smooth. No bump bigger than a few billionths of a meter high. Equally amazing are these. Fused silica fibers, a few times the thickness of a human hair. Designed by the University of Glasgow in conjunction with scientists from other British universities. They isolate the mirror completely, so it hangs perfectly still. You could say that in there is the quietest place on Earth. Despite this, outside events do sometimes interfere with the work here, as I witnessed for myself.
I've wandered into the control room here at LIGO because I'm told something kicked off a few hours ago, and they're all very busy. The image that's flickering up there is not meant to be like that. Essentially, what they've picked up is a seismic disturbance, an earthquake. Now, that's not an earthquake down the road. It started on the other side of the planet, in Japan. So it just gives us a sense of the tremendous challenges faced by LIGO and the team here, and the level of sensitivity needed, that an earthquake on the other side of the Earth can disrupt their measurements and have to reset everything all over again.
One of the scientists involved in developing this extraordinary place put it quite succinctly. Once we were blind, but now we can see.
Throughout the entire history of astronomy, we've studied gravity and how it affects matter in the universe and how it warps space-time, but only by looking at the light that enters our telescopes. Now, for the first time, we can study the universe in a different way. The discovery of gravitational waves means we can see objects that cause extreme warping of space-time and its effect on gravity directly. This essentially opens up a new era in astronomy. It gives us a new way of looking out at the universe.
Professor Sheila Rowan was one of the scientists who spearheaded the British effort for LIGO. For her and her colleagues, gravitational wave detection is just in its infancy. New instruments, even more sensitive than LIGO, are now being developed.
There's so much that we don't understand about the universe that we live in, and this has suddenly given us a new tool, a new way to probe the dark processes in the universe. Because every time we make the observatories more sensitive, we can sense gravitational wave signals from further away, from farther out in the universe, from further back in cosmic history. Things like supermassive black holes spiralling in to collide, small black holes orbiting round supermassive black holes, tracing out the dents in space-time of those supermassive objects. A long-term goal is to probe back further towards what we think of as the Big Bang, the earliest moments that we understand of the universe as we know it.
If you think about it, time and time again in the history of science, unlocking the mysteries of gravity have led to a deeper understanding of the universe. Galileo and his ramp, Newton and his apple, Einstein and the falling man in the lift. Each of these characters challenged the scientific consensus of the day. And even today, understanding the true nature of gravity remains one of the biggest challenges in science.
Which brings me back to the smartphone app. And it's at this point that our story, for me at least, takes a completely unexpected turn. Unfortunately, it's all gone a bit pear-shaped.
Okay, so here's what's happened. A couple of months ago, we launched the app, and it was all going really well. Thousands of people downloaded it and have been sending us their results. We've been collecting the data to create this nationwide map to show how time flows at different rates for different people around the country. Unfortunately, I've just realized there's a big problem. You see, I was going over the scientific literature, and I came across this subtle point about relativity, which basically made me sit bolt upright. There was this horrible, dawning realization that I've made a mistake in the equations that get fed into the app.
So what this means is all the results we've been gathering are wrong.
The issue lies in the strange and subtle effects of Einstein's theories of relativity, and it's fundamental to the way time flows across the surface of the globe. Now, what if I use my smartphone app where I live here on the south coast of England, and then go and spend a few days down near the equator, say here on the west coast of Africa?
Now, we know from the road trip that gravity is weaker by the equator. So that means time ticks faster there.
But there's another important factor we have to take into account: movement. You see, when I'm here near the equator, I'm moving more quickly than I was back in Britain because of the rotation of the Earth.
Einstein says movement slows down time, so clocks will tick slower at the equator.
This is where the error crept in. You see, I had taken into account these two effects, but I'd missed a crucial point. They cancel each other out exactly. In fact, the Earth bulges out exactly the right amount for its rotational speed to make sure they cancel out. So all clocks on the surface of the Earth at sea level tick at exactly the same rate.
So now I'm having to go right back to square one and completely rewrite the equations for the app. And to test if it's working, I'm going to use it over the course of a normal working week.
This is where I live. This is Portsmouth, which means I'm very close to sea level. And this is how I start most mornings, catching the train to work.
The app records my speed as I'm on the train and calculates how this slows down my personal clock.
I think the train journey should have slowed my time down by a few trillionths of a second.
I'm heading for the BBC's headquarters in central London, and gravity should be a bit weaker here.
I'm a few meters above sea level, I guess, here, and so there'll be a speed up of my time because of altitude.
The app compares the way my time flows with a stationary clock at sea level. So what's my result? On an average day, my movement makes me age slower by 1/3 of a nanosecond. That's 1/3 of a billionth of a second. But the weaker gravity I'm in means I age faster. Overall, 1/2 a nanosecond faster. I've also given the app to some other volunteers to compare how they age over an average day. Nick flies cargo planes. He flies from Chicago to Germany.
Tomorrow morning, we have to leave to go first to Milan and then on to Tokyo.
His travel slows down his aging, but much weaker gravity at high altitude speeds his clock up by just a bit more. Overall, he's aging 5 nanoseconds faster than a stationary clock at sea level. Vanessa runs a pub in the Yorkshire Dales.
I'm going to take you outside to see the weather conditions here. So here we are outside the Tan Hill Inn. We live right in the middle of the National Park on the moor.
The Tan Hill Inn is famous as Britain's highest altitude pub, at over 500 metres above sea level.
We don't have any neighbours, we just have sheep.
Her altitude means she ages faster every day by around 4 nanoseconds, compared to someone at sea level. There's Kevin, a mountaineer in the Highlands.
I'm on a mountain in Glencoe called Scornahulia. I've been at an altitude generally of between 2,000 to 3,000 feet for a lot of the day. Throughout the day, I've just been logging onto the phone, logging onto the app, and just checking it out and having a look, and I've been watching it get bigger, watching the value get bigger and bigger, so it's been quite a lot of fun.
On an average day of climbing, Kevin's personal clock goes faster by 1 nanosecond. Gary works for a Scottish water retailer.
My job takes me all over the UK, dealing with energy consultants and energy brokers. As far up north as Inverness, as far down south as London. Approximately do about 1,000 miles a week, sometimes more, depending on the number of meetings I have.
Gary's car journeys do slow his time down a bit, but being above sea level means he still ages faster by 3/4 of a nanosecond. Our final volunteer is Walter. He lives close to sea level at the iconic John O'Groats.
I run a tourism business and I started about 50 years ago. So when people come here, they can actually physically speak to someone who's been born in John O'Groats. And if they ask questions, I can tell them all sorts of useless information because I'm full of useless information.
So our final results show that if you want to age more slowly, try to live near sea level, like Walter. Or there is another way to do it. Get a job on the International Space Station. Its 17,000-mile-an-hour orbit will give you a boost.
We did the math for the astronauts. Every month, you are about 1 millisecond younger. So, 1,000th of a second. So after 6 months, you are that much younger than people on Earth. So I'm younger than I should be. I hope I look it.
Of course, for us on Earth, time dilation is so utterly minuscule, a few billionths of a second between us, you might think it's too frivolous to even bother about. And yet, in the long and difficult process of designing the app, I've come to an extraordinary conclusion. The different ways that time flows may not be some quirky byproduct of gravity. It may actually be gravity. It may be the cause of gravity, the reason why objects fall.
One of the colleagues I've been consulting is Kip Thorne. He's one of the world's leading theoretical physicists and a driving force behind the creation of LIGO. While I was going back over some of the basic physics behind the app, I came across an intriguing idea of his. It's a very interesting and different way of describing gravity.
This is what Kip says. Everything likes to live where it'll age the most slowly, and gravity pulls it there. Kip's based at Caltech in California and is one of the most respected theoretical physicists in the world.
Firstly, Kip, a serious thank you for helping out with the debacle over the app.
Well, I sympathize. I've made so many errors in my own over the years that I am totally sympathetic.
One of the things that struck me thinking about this is something you wrote, Kip. You said, everything likes to live where it'll age the most slowly, and gravity pulls it there. Was this a way of explaining something that you felt was a neat explanation, or is there something deeply profound about that?
I think there is something deeply profound in some sense, but it's a lovely description of Einstein's first major insight about gravity in 1912. He realized that gravity that we feel on Earth is due to a slowing of time on Earth.
So time comes before gravity in that sense. You know, on the Earth's surface, time runs more slowly, and that accounts for why gravity wants to keep us there.
Well, I think in a very deep sense this is true. Objects want to fall, that the flow of time, or the rate of flow of time, is the thing that produces the gravity. It is the thing that is ultimately responsible for the fall.
So somehow it's in the nature of all objects to move towards a region where time runs slower. Kip's formulation works anywhere in the universe where the gravitational field is such as on Earth.
The difference in the rate of flow of time is tiny. At high altitude and on the surface of the Earth, the difference in the rate of flow of time is 1 second in 100 years. That's not very much, but that is enough. That is precisely the right amount to produce the gravitational pull that we feel and produce the accelerations we're talking about.
Wow, okay, I need to go and write this one down.
So my investigation deep into the weird ways of gravity has finally left me face to face with one of the greatest mysteries in all of physics: the nature of time itself.
It sounds like such a simple question. Why does the apple fall? And yet hundreds of years of scientific inquiry investigating this single action have led us to completely redefine the way we think about the very nature of space and time. And now I've been presented with this extraordinary proposition that somehow, in some profound way, the apple falls because it's seeking out the place where time runs the slowest. So does gravity dictate the flow of time, or does time itself define gravity? Could this hint to fundamental new laws of physics as yet undiscovered? I think I'm going to have to think about this a bit more.
This is a film about one very simple question. How did we get here? These are the elements and compounds from which all humans are made. They're incredibly, almost embarrassingly common. In fact, almost 99% of the human body is a mixture of air, water, coal and chalk, with traces of other slightly more exotic elements like iron, zinc, phosphorus and sulfur. In fact, I've estimated that the elements which make up the average human cost at most a few pounds. But somehow, trillions of these very ordinary atoms conspire miraculously to organize themselves into thinking, breathing, living human beings. How the wonders of creation are assembled from such simple building blocks is surely the most intriguing question we can ask.
You may think that answering it is beyond the realm of science, but that's changing. For the first time, I believe, science has pushed past religion and philosophy in daring to tackle this most fundamental of questions.
This film is the story of a series of bizarre and interconnected discoveries that revealed a hidden face of nature. That woven into its simplest and most basic laws is a power to be unpredictable. It's about how inanimate matter with no purpose or design can spontaneously create exquisite beauty. It's about how the same laws that make the universe chaotic and unpredictable can turn simple dust into human beings. It's about the discovery that there is a strange and unexpected relationship between order and chaos. The natural world really is one great, blooming, buzzing confusion. It's a mess of quirky shapes and blotches. What patterns there are never quite regular and never seem to repeat exactly. The idea that all this mayhem, all this chaos, is underpinned, indeed determined, by mathematical rules, and that we can work out what those rules might be, runs counter to our most dearly held intuitions. So, not surprisingly, the first man to really take on the momentous task of unraveling nature's mysterious mathematics had a very special and unusual mind. He was both a great scientist and a tragic hero. He was born in 1912 in London. His name was Alan Turing.
Alan Turing was a remarkable man, one of the greatest mathematicians who ever lived. He discovered many of the fundamental ideas that underpin the modern computer. Also, during the Second World War, he worked here at Bletchley Park, just outside today's Milton Keynes, in what was then a secret government project called Station X, which was set up to crack the German military codes.
The Station X codebreakers proved highly effective, and Turing's contribution was crucial. The work he personally did to crack German naval codes saved thousands of Allied lives and was a turning point in the war.
But code breaking was just one aspect of Turing's genius, just one part of his uncanny ability to see patterns that are hidden from the rest of us. For Turing, the natural world offered up the ultimate codes, and over the course of his life, he'd come tantalizingly close to cracking them.
Turing was a very original person, and he had realized that there was this possibility that simple mathematical equations might describe aspects of the biological world, and no one had thought of that before.
Of all nature's mysteries, the one that fascinated Turing most was the idea that there might be a mathematical basis to human intelligence. Turing had very personal reasons for believing in this.
It was the death of this young man, Christopher Morcom, who Alan Turing, well, he was gay, and it'd been a great emotional thing of his life at that point. Christopher Morcom suddenly died. And Alan Turing was obviously he was very emotionally disturbed by this, but you can see that he wanted to put this in an intellectual context, a scientific context. And the question he wanted to put into context was, what happens to the mind? What happens to it? What is it?
Turing became convinced that mathematics could be used to describe biological systems and ultimately intelligence. This fascination would give rise to the modern computer, and later in Turing's life, an even more radical idea. The idea that a simple mathematical description could be given for a mysterious process that takes place in an embryo. The process is called morphogenesis, and it's very puzzling. At first, all the cells in the embryo are identical. Then, the cells begin to clump together and also become different from each other. How does this happen? With no thought, no central coordination. How do cells that start off identical know to become, say, skin, while others become part of an eye? Morphogenesis is a spectacular example of something called self-organization. And before Turing, no one had a clue how it worked. Then, in 1952, Turing published this, his paper with the world's first mathematical explanation for morphogenesis. The sheer chutzpah of this paper was staggering. In it, Turing used a mathematical equation of the kind normally seen in papers on astronomy or atomic physics to describe a living process. No one had done anything like this. Crucially, Turing's equations did, for the first time, describe how a biological system could self-organize. They showed that something smooth and featureless can develop features.
One of the astonishing things about Turing's work was that starting with a description of really very simple processes that were governed by very simple equations, by putting these together, suddenly complexity emerged. The pattern suddenly came out as a natural consequence. And I think in many ways this was very, very unexpected.
In essence, Turing's equations described something quite familiar, but which no one had thought of in the context of biology before. Think of the way a steady wind blowing across sand creates all kinds of shapes. The grains self-organize into ripples, waves, and dunes. This happens even though the grains are virtually identical and have no knowledge of the shapes they become part of. Turing argued that in a very similar way, chemicals seeping across an embryo might cause its cells to self-organize into different organs. These are Turing's own very rough scribblings of how this might work. They show how a completely featureless chemical soup can evolve these strange blobs and patches. In his paper, he refined his sketches to show how his equations could spontaneously create markings similar to those on the skins of animals.
Turing went around showing people pictures saying, doesn't this look a bit like the patterns on a cow? And everyone sort of, what is this man on about? But actually, he knew what he was doing. Because, yeah, indeed, they did look like the patterns on a cow, and that's one of the reasons why cows have this sort of dappled pattern or whatever. So an area where mathematics had never been used before, pattern formation in biology, animal markings, suddenly the door was opened and we could see that mathematics might be useful in that sort of area. So even though Turing's exact equations are not the full story, they are the first piece of mathematical work that showed there was any possibility of doing this kind of thing.
Of course, we now know that morphogenesis is much more complicated than the process Turing's equations describe. In fact, the precise mechanism of how DNA molecules in our cells interact with other chemicals is still fiercely debated by scientists. But Turing's idea that whatever is going on is deep down a simple mathematical process was truly revolutionary.
Well, I think Alan Turing's paper is probably the cornerstone in the whole idea of how morphogenesis works. What it does is it provides us with a mechanism, something that Darwin didn't, for how pattern emerges. Darwin, of course, tells us that once you have a pattern and it is coded for in the genes, that may or may not be passed on depending on circumstances. But what it doesn't do is explain where that pattern comes from in the first place. That's the real mystery. And so what Turing had done was to suddenly provide an accessible chemical mechanism for doing this. That was amazing.
Turing was onto a really big, bold idea. But sadly, we can only speculate how his extraordinary mind would have developed his idea. Because shortly after his groundbreaking paper on morphogenesis, a dreadful and completely avoidable tragedy destroyed his life.
After his work breaking codes at Bletchley Park, you might well have assumed that Turing would have been honoured by the country he did so much to protect. This couldn't be further from the truth. What happened to him after the war was a great tragedy, and one of the most shameful episodes in the history of British science.
The same year Turing published his morphogenesis paper, he had a brief affair with a man called Arnold Murray. The affair went sour, and Murray was involved in a burglary at Turing's house. But when Turing reported this to the police, they arrested him as well as Murray. In court, the prosecution then argued that Turing, with his university education, had led Murray astray. He was convicted of gross indecency. The judge then offered Turing a dreadful choice.
He could either go to prison or sign up to a regime of female hormone injections to cure him of his homosexuality. He chose the latter, and it was to send him into a spiral of depression. On the 8th of June 1954, Turing's body was found by his cleaner. He died the day before by taking a bite from an apple he'd laced with cyanide, ending his own life.
Alan Turing died aged just 41. The loss to science is incalculable. Turing would never know that his ideas would inspire an entirely new mathematical approach to biology, and that scientists would find equations like his really do explain many of the shapes that appear on living organisms. Looking back, we now know Turing had really grasped the idea that the wonders of creation are derived from the simplest of rules. He had, perhaps unexpectedly, taken the first step to a new kind of science. The next step in this story was just as unexpected, and in many ways, just as tragic as Turing's.
In the early 1950s, around the time of Turing's seminal paper on morphogenesis, a brilliant Russian chemist by the name of Boris Belousov was beginning his own investigations into the chemistry of nature. Deep behind the Iron Curtain, in a lab at the Soviet Ministry of Health, he was beginning to investigate the way our bodies extract energy from sugars. Just like Turing, Belousov was working on a personal project, having just finished a distinguished career as a scientist in the military. In his lab, Belousov had formulated a mixture of chemicals to mimic one part of the process of glucose absorption in the body. The mix of chemicals sat on the lab bench in front of him, clear and colourless while being shaken. As he mixed in the final chemical, the whole solution changed colour. Now, this isn't particularly remarkable. If we mix ink into water, it changes colour. But then something happened that made no sense at all. The mixture began to go clear again. Belousov was astounded. Chemicals can mix together and react, but they shouldn't be able to go back on themselves to apparently unmix without intervention. You can change from a clear mixture to a coloured mixture, fine, but surely not back again. And it got weirder. Belousov's chemicals didn't just spontaneously go into reverse. They oscillated. They switched back and forth from coloured to clear, as if they were being driven by some sort of hidden chemical metronome. With meticulous care, Belousov repeated his experiment again and again. It was the same every time. His mixture would cycle from clear to coloured and back again, repeatedly. He discovered something that was almost like magic, a physical process that seemed to violate the laws of nature. Convinced he'd discovered something of great importance, Belousov wrote up his findings, keen to share his discovery with the wider world. But when he submitted his paper to a leading Russian scientific journal, he received a wholly unexpected and damning response. The editor of the journal told Belousov that his findings in the lab were quite simply impossible. They contravened the fundamental laws of physics. The only explanation was that Belousov had made a mistake in his experiment, and the work was simply not fit for publication. The rejection crushed Belousov. Deeply insulted by the suggestion his work had been botched, he abandoned his experiments. Soon, he gave up science altogether. The tragic irony was that, divided as they were by the Iron Curtain, Belousov never encountered Turing's work. For if he had, he would have been completely vindicated. It turns out that Belousov's oscillating chemicals, far from contravening the laws of physics, were actually a real-world example of precisely the behavior Turing's equations predicted. While the connection might not appear obvious at first sight, other scientists showed that if you left a variation of Belousov's chemicals unstirred in a petri dish, instead of simply oscillating, they self-organize into shapes. In fact, they go beyond Turing's simple blobs and stripes to create stunningly beautiful structures and patterns out of nowhere.
The amazing and very unexpected thing about the BZ reaction is that someone had discovered a system which essentially reproduces the Turing equations. And so from what looks like a very, very bland solution emerge these astonishing patterns of waves and scrolls and spirals.
Now, this is emphatically not abstract science. The way Belousov's chemicals move as coordinated waves is exactly the way our heart cells are coordinated as they beat. Animal skins and heartbeats. Self-organization seems to operate all over the natural world. So why were the scientific community in Turing and Belousov's day so uninterested or even hostile to this astonishing and beautiful idea? Well, the reason was all too human. Mainstream scientists simply didn't like it. To them, it seemed to run counter to science and all that it had achieved. To change that view would require a truly shocking and completely unexpected discovery. In essence, by the beginning of the 20th century, scientists saw the universe as a giant, complicated mechanical device. Kind of a supersized version of this orrery. The idea was that the universe is a huge and intricate machine that obeys orderly mathematical rules. If you knew the rules of how the machine was configured to start with, as you turned the handle over and over again, it would behave in an entirely predictable way.
Back in the times of Isaac Newton, when people were discovering the laws that drove the universe, they came up with this kind of metaphor of a clockwork universe. The universe looked like a machine which had been set going at the instant of creation and just followed the rules and ticked along. And it was a complicated machine, and therefore complicated things happened. But once you set it going, it would only do one thing. And the message that people drew from this was that anything describable by mathematical rules must actually basically be fairly simple.
Find the mathematics that describes a system, and you can then predict how that system will unfold. That was the big idea. It began with Newton's law of gravity, which can be used to predict how a planet moves around the sun. Scientists soon found many other equations just like it.
Newtonian physics seemed like the ultimate crystal ball. It held up the tantalizing possibility that the future could in principle be known. The more careful your measurements are today, the better you can predict what will happen tomorrow.
But Newtonianism had a dangerous consequence. If a nice mathematical system that worked in a similar way to my orrery did sometimes become unpredictable, scientists assumed some malign outside force was causing it. Perhaps dirt had got in, perhaps the cogs were wearing out, or perhaps someone had tampered with it.
Basically, we used to think if you saw very irregular behaviour in some problem you're working on, this must be the result of some sort of random outside influences. It couldn't be internally generated. It wasn't an intrinsic part of the problem. It was some other thing impacting on it.
Looked at from this point of view, the whole idea of self-organization seemed absurd. The idea that patterns of the kind Turing and Belousov had found could appear of their own accord without any outside influence was a complete taboo.
6, 5, 4, 3.
The only way for self-organization to be accepted was for the domineering Newtonian view to collapse. But that seemed very unlikely. After all, by the late 60s, it had delivered all the wonders of the modern age.
Beautiful view. Isn't that something? Magnificent desolation.
But then, at the same time as the moon mission, a small group of scientists all ardent Newtonians, quite unexpectedly found something wasn't right. Not right at all.
During the second half of the 20th century, a devil was found in the detail. A devil that would ultimately shatter the Newtonian dream and plunge us literally into chaos.
Ironically, the event that forced scientists to take self-organization seriously was the discovery of a phenomenon known as chaos. Chaos is one of the most overused words in English, but in science it has a very specific meaning. It says that a system that is completely described by mathematical equations is more than capable of being unpredictable without any outside interference whatsoever.
There's a widespread misapprehension that chaos is just somehow saying the very familiar fact that everything's complicated. I mean, the nitwit chaoticist in Jurassic Park was under that confusion. It's something much simpler and yet much more complicated than that. It says some very, very simple rules or equations with nothing random in them, and completely determined, we know everything about the rule, can have outcomes that are entirely unpredictable.
Chaos is one of the most unwelcome discoveries in science. The man who forced the scientific community to confront it was an American meteorologist called Edward Lorenz. In the early 1960s, he tried to find mathematical equations that could help predict the weather. Like all his contemporaries, he believed that in principle, the weather system was no different to my orrery. A mechanical system that could be described and predicted mathematically. But he was wrong. When Lorenz wrote down what looked like perfectly simple mathematical equations to describe the movement of air currents, they didn't do what they were supposed to. They made no useful predictions whatsoever.
It was as if the lightest breath of wind one day could make the difference a month later between a snowstorm and a perfectly sunny day.
How can a simple system that works in the regular clockwork manner of my orrery become unpredictable? It's all down to how it's configured, how the gears are connected. In essence, under certain circumstances, the tiniest difference in the starting positions of the cogs, differences that are too small to measure, can get bigger and bigger with each turn of the handle. With each step in the process, the system then moves further and further away from where you thought it was going. Lorenz captured this radical idea in an influential talk he gave called "Does the Flap of a Butterfly's Wings in Brazil Set Off a Tornado in Texas?"
It was a powerful and evocative image, and within months, a new phrase had entered our language: the butterfly effect.
And the butterfly effect, the hallmark of all chaotic systems, started turning up everywhere. In the early 70s, a young Australian called Robert May was investigating a mathematical equation that modelled how animal populations changed over time. But here too lurked the dreaded butterfly effect. Immeasurably small changes to the rate at which the animals reproduced could sometimes have huge consequences on their overall population. Numbers could go up and down wildly for no obvious reason. The idea that a mathematical equation gave you the power to predict how a system will behave was dead.
In some sense, this is the end of the Newtonian dream. Because when I was a graduate student, the belief was, as we got more and more computer power, we'd be able to solve ever more complicated sets of equations. But this said that's not necessarily true. You could have the simplest equations you can think of, with nothing random in them. You know everything. And yet, if they have behavior that gives you chaotic solutions, then you can never know the starting point accurately enough.
Centuries of scientific certainty dissolved in just a few short years. The truth of the clockwork universe turned out to be just an illusion. Something which had seemed a logical certainty revealed itself merely as an act of faith. And what's worse, the truth had been staring us in the face all the time, because chaos is everywhere. It seemed unpredictability was hardwired into every aspect of the world we live in. The global climate could dramatically change in the course of a few short years. The stock market could crash without warning. We could be wiped from the face of the planet overnight, and there is nothing anyone could do about it. Unfortunately, I have to tell you that all of this is true. And yet, to be scared of chaos is pointless. It's woven into the basic laws of physics. And we really all have to accept it as a fact of life.
The idea of chaos really did have a big impact over a period of about 20 or 30 years, because it changed the way everyone thought about what they were doing in science. It changed it to the point that they forgot that they'd ever believed otherwise. What chaos did was to show us that the possibilities inherent in the simple mathematics are much broader and much more general than you might imagine. And so a clockwork universe can nonetheless behave in the rich, complex way that we experience.
The discovery of chaos was a real turning point in the history of science. As it tore down the Newtonian dream, scientists began to look more favorably at Turing and Belousov's work on spontaneous pattern formation. And perhaps more importantly, as they did so, they realized something truly astonishing. That there was a very deep and unexpected link, a truly cosmic connection between nature's strange power to self-organize and the chaotic consequences of the butterfly effect. Between them, Turing, Belousov, May, and Lorentz had all discovered different faces of just one really big idea. They discovered that the natural world could be deeply, profoundly unpredictable. But the very same things that make it unpredictable also allow it to create pattern and structure. Order and chaos. It seems the two are more deeply linked than we could have ever imagined. So how is this possible? What do phenomena as apparently different as the patterns in Belousov's chemicals and the weather have in common? First, though both systems behave in very complicated ways, they are both based on surprisingly simple mathematical rules. Secondly, these rules have a unique property, a property that's often referred to as coupling or feedback. To show you what I mean, to show you both order and chaos can emerge on their own from a simple system with feedback, I'm going to do what seems at first glance like a rather trivial experiment. This screen behind me is connected up to the camera that's filming me. But the camera in turn is filming me with the screen. This creates a loop
with multiple copies of me appearing on the screen. This is a classic example of a feedback loop. We get a picture in a picture in a picture. At first it seems fairly predictable, but as we zoom the camera in, some pretty strange things begin to happen. The first thing I notice is that the object I'm filming stops bearing much resemblance to what now appears on the screen. Small changes in the movement of the match become rapidly amplified as they loop round from the camera to the screen and back to the camera. So even though I can describe each step in the process mathematically, I still have no way of predicting how tiny changes in the flickering of the flame will end up in the final image. This is the butterfly effect in action. But now here comes the spooky bit. With just a slight tweak to the system, these strange and rather beautiful patterns begin to emerge. The same system, one that's based on simple rules with feedback, produces chaos and order.
The same mathematics is generating chaotic behaviour and patterned behaviour. This changes completely how you think about all of this. The idea that there are regularities in nature and then totally separately from them are irregularities and these are just two different things. It's just not true. These are two ends of a spectrum of behaviour which can be generated by the same kind of mathematics. And it's the closest thing we have at the moment to the kind of true mathematics of nature.
Well, I think one of the great take-home messages from Turing's work and from the discoveries in chemistry and biology and so on is that ultimately pattern formation seems to be woven very, very deeply into the fabric of the universe. And it actually takes some very, very simple and familiar processes like diffusion, like the rates of chemical reactions. And the interplay between them naturally gives rise to pattern. So pattern is everywhere. It's just waiting to happen.
From the 70s on, more and more scientists began to embrace the concept that chaos and pattern are built into nature's most basic rules. But one scientist, more than any other, brought a fundamentally new understanding to this astonishing and often puzzling idea. He was a colourful character and something of a maverick. His name is Benoit Mandelbrot. Benoit Mandelbrot wasn't an ordinary child. He skipped the first 2 years of school, and as a Jew in war-torn Europe, his education was very disrupted. He was largely self-taught or tutored by relatives. He never formally learned the alphabet, or even multiplication beyond the 5 times table. But like Alan Turing, Mandelbrot had a gift for seeing nature's hidden patterns. He could see rules where the rest of us see anarchy. He could see form and structure where the rest of us just see a shapeless mess. And above all, he could see that a strange new kind of mathematics underpinned the whole of nature. Mandelbrot's lifelong quest was to find a simple mathematical basis for the rough and irregular shapes of the real world.
Mandelbrot was working for IBM and he was not in the normal academic environment. And he was working on a whole pile of different problems about irregularities in nature, in the financial markets, all over the place. And I think at some point it dawned on him that everything he was doing seemed to be really parts of the same big picture. And he was a sufficiently original and unusual person that he realised that pursuing this big picture was what he really wanted to do.
To Mandelbrot, it seemed perverse that mathematicians had spent centuries
contemplating idealized shapes like straight lines or perfect circles, and yet had no proper or systematic way of describing the rough and imperfect shapes that dominate the real world.
Take this pebble. Is it a sphere or a cube? Or maybe a bit of both? And what about something much bigger? Look at the arch behind me. From a distance, it looks like a semicircle. But up close, we see that it's bent and crooked. So what shape is it?
Mandelbrot asked if there's something unique that defines all the varied shapes in nature. Do the fluffy surfaces of clouds, the branches in trees and rivers, the crinkled edges of shorelines share a common mathematical feature? Well, they do. Underlying nearly all the shapes in the natural world is a mathematical principle known as self-similarity. This describes anything in which the same shape is repeated over and over again at smaller and smaller scales. A great example are the branches of trees. They fork and fork again, repeating that simple process over and over at smaller and smaller scales. The same branching principle applies in the structure of our lungs and the way our blood vessels are distributed throughout our bodies. It even describes how rivers split into ever smaller streams. And nature can repeat all sorts of shapes in this way. Look at this Romanesco broccoli. Its overall structure is made up of a series of repeating cones at smaller and smaller scales. Mandelbrot realized self-similarity was the basis of an entirely new kind of geometry, and he even gave it a name: fractal.
Now that's a pretty neat observation. But what if you could represent this property of nature in mathematics? What if you could capture its essence to draw a picture? What would that picture look like? Could you use a simple set of mathematical rules to draw an image that didn't look man-made?
The answer would come from Mandelbrot, who had taken a job at IBM in the late 1950s to gain access to its incredible computing power and pursue his obsession with the mathematics of nature. Armed with a new breed of supercomputer, he began investigating a rather curious and strangely simple-looking equation that could be used to draw a very unusual shape.
What I'm about to show you is one of the most remarkable mathematical images ever discovered. Epic doesn't really do it justice. This is the Mandelbrot set. It's been called the thumbprint of God, and when we begin to explore it, you'll understand why.
Just as with the tree or the broccoli, the closer you study this picture, the more detail you see. Each shape within the set contains an infinite number of smaller shapes, baby Mandelbrots that go on forever. Yet all this complexity stems from just one incredibly simple equation. This equation has a very important property. It feeds back on itself. Like a video loop, each output becomes the input for the next go. This feedback means that an incredibly simple mathematical equation can produce a picture of infinite complexity. The really fascinating thing is that the Mandelbrot set isn't just a bizarre mathematical quirk. Its fractal property of being similar at all scales mirrors a fundamental ordering principle in nature. Turing's patterns, Belousov's reaction, and Mandelbrot's fractals are all signposts pointing to a deep underlying natural principle.
When we look at complexities in nature, we tend to ask, where did they come from? There is something in our heads that says complexity does not arise out of simplicity. It must arise from something complicated. We conserve complexity. But what the mathematics in this whole area is telling us is that very simple rules naturally give rise to very complex objects. And so if you look at the object, it looks complex. And you think about the rule that generates it, it's simple. So the same thing is both complex and simple from two different points of view. And that means we have to rethink completely the relation between simplicity and complexity.
Complex systems can be based on simple rules. That's the big revelation. And it's an astonishing idea. It seems to apply all over our world. Look at a flock of birds. Each bird obeys very simple rules, but the flock as a whole does incredibly complicated things, avoiding obstacles, navigating the planet with no single leader or even conscious plan. But amazing though this flock's behavior is, it's impossible to predict how it will behave. It never repeats exactly what it does, even in seemingly identical circumstances. It's just like the Belousov reaction. Each time you run it, the patterns produced are slightly different. They may look similar, but they are never identical. The same is true of video loops and sand dunes. We know they'll produce a certain kind of pattern, but we can't predict the exact shapes. The big question is, can nature's ability to turn simplicity into complexity in this mysterious and unpredictable way explain why life exists? Can it explain how a universe full of simple dust can turn into human beings? How inanimate matter can spawn intelligence?
At first, you might think that this is beyond the remit of science. If nature's rules are really unpredictable, should we simply give up? Absolutely not. In fact, quite the opposite.
Fittingly, the answer to this problem lies in the natural world. All around us, there exists a process that engineers these unpredictable, complex systems and hones them to perform almost miraculous tasks. The process is called evolution.
Evolution has built on these patterns. It's taken them as the raw ingredients. It's combined them together in various ways, experimented to see what works and what doesn't, kept the things that do work, and then built on that. It's a completely unconscious process, but basically that's what's happening.
Everywhere you look, you can see evolution using nature's self-organizing patterns. Our hearts use Belousov-type reactions to regulate how they beat. Our blood vessels are organized like fractals. Even our brain cells interact according to simple rules. The way evolution refines and enriches complex systems is one of the most intriguing ideas in recent science.
My interest in my PhD research in complex systems was to see how complex systems interact with evolution. So on the one hand, you have systems that almost organize themselves as complex systems, so they exhibit order that you wouldn't expect. But on the other hand, you still have to have evolution interact with that to create something that is truly adapted to the environment.
Evolution's mindless yet creative power to develop and shape complex systems is indeed incredible. But it operates on a cosmic timescale. From the first life on Earth to us walking about took in the region of 3.5 billion years. But we now have in our hands a device that can mimic this process on a much shorter timescale. What is the invention I'm talking about? Well, there's a good chance you've been sitting in front of one all day. It is, of course, the computer. Computers today can churn through trillions of calculations per second, and that gives them the power to do something very special. They can simulate evolution. More precisely, computers can use the principles of evolution to shape and refine their own programs, in the same way the natural world uses evolution to shape and refine living organisms. And today, computer scientists find that this evolved software can solve problems that would be beyond the smartest of humans.
One thing that we found, and particularly in our original research, is how powerful evolution is as a system, as an algorithm to create something that is very complex and to create something that's very adaptive.
Torsten and his team's goal was nothing less than to use computerized evolution to create a virtual brain that would control a virtual body. To begin with, they created 100 random brains. As you can see, they weren't up to much. Evolution then took over. The computer selected the brains that were slightly better at moving their bodies and got them to breed.
The algorithm then takes those individuals that do the best and it allows them to create offspring.
The best movers of the next generation were then bred together, and so on and on. Amazingly, after just 10 generations, although they're still a bit unsteady, the figures could walk.
Eventually, miraculously, you actually end up with something that works. The slightly scary thing is you don't know why it works and how it works. You look at that brain and you have no idea actually what's going on because evolution has optimized it automatically.
In 20 generations, evolution had turned this into this. But these evolved computer beings soon went far beyond just walking. They evolved to do things that really are impossible to program conventionally. They react realistically to unexpected events, like being hit or falling over.
Even though we program these algorithms, what actually then happens when it unfolds live, we don't control anymore, and things happen that we never expected. And it's quite a funny feeling that you create these algorithms, but then they do their own thing.
An unthinking process of evolutionary trial and error has created these virtual creatures that can move and react in real time. What we're seeing here is fantastic experimental evidence for the creative power of systems based on simple rules. Watching how computers can unconsciously evolve programs to do things that no human could consciously program is a fantastic example of the power of self-organization. It demonstrates that evolution is itself just like the other systems we've encountered. One based on simple rules and feedback, from which complexity spontaneously emerges. Think about it. The simple rule is that the organism must replicate, with a few random mutations now and again. The feedback comes from the environment, which favors the mutations that are best suited to it. The result is ever-increasing complexity, produced without thought or design.
The interesting thing is that one can move up to a higher level of organization. Once you have organisms that actually have patterns on them, these can be selected for or selected against by processes which are essentially feedbacks. And so evolution itself, the whole Darwinian scheme, is in a sense Turing again, with feedbacks happening through different processes.
And that's the essence of this story. Unthinking, simple rules have the power to create amazingly complex systems without any conscious thought. In that sense, these computer beings are self-organized systems, just like the one Belousov observed happening in his chemicals, just like the ones in sand dunes and the Mandelbrot set, in our lungs, our hearts, in weather, and in the geography of our planet. Design does not need an active, interfering designer. It's an inherent part of the universe.
One of the things that makes people so uncomfortable about this idea of, if you will, spontaneous pattern formation is that somehow or other you don't need a creator, but perhaps a really clever designer. What he would do is to kind of treat the universe like a giant simulation where you set some initial condition and just let the whole thing spontaneously happen in all of its wonder and all of its beauty.
The mathematics of pattern formation shows that the same kind of pattern can show up in an enormous range of different physical, chemical, biological systems. Somewhere deep down inside, it's happening for the same mathematical reason. Implicit in those facts are these beautiful patterns that we see everywhere. This, I think, is a mind-blowing thought.
So what is the ultimate lesson we can take from all this? Well, it's that all the complexity of the universe, all its infinite richness, emerges from mindless, simple rules, repeated over and over again. But remember, powerful though this process is, it's also inherently unpredictable. So, although I can confidently tell you that the future will be amazing, I can also say with scientific certainty that I have no idea what it holds.